Okay, any questions? So I got some questions from people emailing me wondering about the format of the exam. So, hmm, yeah. So basically, for this exam, because some of you guys haven't done a class with Dr. Zom before, um, the exam is typically going to be around 9 pages, I think. Um, Somewhere between, I want to say like 6 to 9 pages. It really depends on like how dense the information is. But whatever you see in the practice exam is exactly the length you're gonna get. Um, in terms of how accurate the practice exam is, it is pretty accurate. If you just go through that, you like it's very important that you go through the practice exam. I would say, like a good 50% of the questions are gonna come from the practice exam. Um, and then after that, the other important thing, so your main resources you need to use are the practice exam and the practice quizzes and your actual quizzes. If you do all of those, I would say you have about 75% of the material there. And then the rest of the material is going to be small questions that are related to those questions, and you can find them in your notes and stuff. So, but the first most important thing to do is go over all of the quizzes and the practice exam. Then after that, you can look through your notes for other things. Um, you should pay attention to things that you find a little bit more complicated, like memorizing that sheet about like what's activating, what's deactivating. That's really important. All right, so someone had a question. Let me open that up. So someone had a question from the practice exam, um, question 3 on the practice exam. So everyone just get that up so you can go along with me. Okay, so by question 3, I need to know a little bit more specifically which question 3, because there's question 3A and B. Which one? Or is it both that you need to know about? Let's just do both. Okay, A. All right, so question 3 is something that you'll definitely get on the exam. So what it is it says, well, here's a whole bunch of possible, okay, my pencil is not charged. But it basically gives you a whole bunch of possible functional groups. And then it asks you like about the activation levels and about how those could tell you a hint of like what that functional group is. So the functional groups we're dealing with here are CF3, CH3, CH3, 3, OCH3, H, and Br. Okay, so the first one is a benzene ring that has something, functional group A on it. The ortho position is 0.003. The meta position is 0.001. Oh no, it's, yeah, 0001. And the para position is 0.004. So when we look at this is not a very activating group, right? This is actually the easiest one that you'll see, and it should be like so easy for you to recognize this. Basically, it's not very activating because all these numbers are extremely small, right? If you look at the one below, those are really, really small. But like some of them will have like 70 in one position. Okay. So having 0.004, 003, that's really, really low. But you'll notice that this is what? Mubarka. What kind of directing is this group? What way does it direct?
Orthopera?
It directs orthopara, yes. But it's very, 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 very not very activating at all. So what do you think it is?
BR?
Yes, it's a halogen. So that's how we know that it's a halogen, because it's very, very little activation, but it's also orthopara. Okay. Any other questions? Okay. So something that someone brought up, question 4 last time, I thought it was really, really good. And I don't know if you guys saw like why this happens, but I was gonna point out, like, if you guys watched the other video or if you were there last Sunday, this is really important. Question 4. So question 4 basically shows that there's this molecule right here, and basically there's also a double bond that's conjugated to it there. So when this reacts with HBr, your instinct is going to be to put Br in the benzylic position, right? So you're going to go, okay, Br attaches. We're going to try to make Br, oops. And I'm doing this in red because I want you guys to know it's wrong. You're going to try to make Br come here, because that's a benzylic position. But there's an even more stable position, and that's a rearrangement. So I'll show you why that happens. So basically, the double bond reaches out, grabs the hydrogen, Br breaks off. So what we get is we get this. And where is the hydrogen? The hydrogen went to this position because it follows Mark's rule. And that means we have a positive charge here. Now, this positive charge is very, very likely to rearrange. So what's going to happen is that this double bond is going to flip here, take that position, and what that causes to happen is that now the positive charge is up here. And that's really good because not only is it allylic to like it's like allylic to 2 double bonds, but it's also a tertiary position. So this is actually better. So from there, the Br is just going to come back when it gets to that position. So this is just like one of those things that like it's a little tricky and you should watch out for it. Okay. Oh, no double bond. Okay. Wait, yes. Oops. There should be a double bond here. Okay. So anyways, that's one of the things to watch out for. But I wanted to contrast that with like a situation where rearrangement isn't possible, you know. Like if I had this, which is another benzylic ring, and let's say that it had a double bond like this. This is styrene, right? And so let's say I reacted this with HBr. Well, in this case, it would grab the hydrogen, Br would come off, you would get positive charge here, hydrogen here, and then the Br would just come there because there's no possible rearrangement for this. Or at least it's not a very good rearrangement. This is a benzylic position, so it's pretty good. All right. So those are the two situations kind of and how to tell them apart. So someone said, can we go over the second part of 3? So yeah, going back up to question 3, another question that was asked right after that. So that was question 3A. So question 3B, how do we do question 3B? So for question 3B, the difference is in the numbers, of course. So the numbers here for the ortho position is 4.5 times 10 to the negative 5. And then the meta position is 67 times 10 to the negative 5. The para position is 7.5 times 10 to the negative 5. So that kind of tells us that this is deactivating, right? Because it's such a small number, it's such a tiny number that it's deactivating. So we know that it must be deactivating, but we also know that it has to be meta-directing. Why? Because that meta position is so much stronger than the ortho or para position. So that can rule out your halogen. Also, the halogens aren't quite that small. So then you just open up or you should have memorized it by now for sure. Which of these are deactivating? So the most deactivating one would the only deactivating one, extremely deactivating one is CF3, right? And this just comes from knowing. Okay. No problem. Any other questions? Okay. So I'm gonna So yeah, so JD has an interesting question. What if everything is one? So like what if he gave you um this and he said here is X and this position is one, this position is one, this position is one. Tell me privately in the chat what you think that group would be. Good. So I have 5 answers so far and everyone's saying hydrogen. You are right because why? Because hydrogen is neither activating nor deactivating. It's kind of like the standard. And hydrogen basically is neither, it doesn't really direct anywhere. It's just, it would be like a mess if you just had like a benzene ring and but I mean, it wouldn't really be a mess because there's nothing to differentiate one from another. So it would just go anywhere, you know what I mean? And it's all the same wherever it goes. All right. So I'm not getting any other questions though. So I think if you guys have any questions, let me know. I'm going to go into my email because I got a whole bunch of questions from someone earlier and I'm going to answer them. Um, I'm not sure if I'll be able to answer them satisfactorily because uh, okay. So the person who asked the questions isn't here, so I'm just going to be kind of hoping that I'm answering it good enough for the recording. Oh, okay. So someone who's here right now just asked a question, so I'm going to go off of that. So someone wants me to do the whole of page 4. Oh, no, no, no. Just O. Question O on page 4. Perfect. Okay. So O on page 4, we're starting out benzene ring, and this is attached to CH3 2. So what is that? That is basically, you can redraw it in bond line if you want. I find that nice. And let's talk about what this reacts with. So first of all, it's reacting with MBS. Then it's going to react with NaET, NaOT, OET. So it's basically, we'll talk about what that is in a second. And it also reacts with B2H6 and H2O2. All right, so here, the first step, MBS. So what do we know about MBS? MBS adds a bromine, and it adds a bromine to the most stable position. So I'm just gonna draw this again. Obviously, like you're gonna have to add a bromine to here, which is the benzylic position. It's also tertiary, so it's extremely stable. Next, we're gonna do NaET, OET. So how do we decode this? Some of us might not know. Some of us might, we might have a sense for what it is already, but Like, what if you just didn't know? So what does ET stand for? ET stands for ethyl. So I could write this as NaO CH2 CH3. This is your ethyl. Okay. So looking at this, what is this? It's basically a strong base, right? Because Na is a spectator ion. You can always just cross out an Na when you see one. So knowing now that that's a strong base, what is it going to do? It's going to protonate the Br and form a double bond. So that's the next step. And that's what we're going to get. Then after that, B2H6H2O2, that should be very familiar to you. That's antimark, the addition of an H and an OH. So we have a double bond here. We're going to add an H and an OH. So it's antimark, so the H goes to the place with the least hydrogen, so that means the OH goes there. And that's your answer. Is that good? Okay. All right. So again, like if you have any questions, send them in the chat. I'm going to be going back to this email that I got. So the first question is about MBS. How does MBS work? So MBS, like I just talked about a second ago, MBS is going to add one bromine to the most stable position. Okay. So, you know, wherever that may be, it's just going to add one bromine to the most stable position. So sometimes he would give us these practices a while ago where it was like this, like that. Okay. And basically when you react this with MBS, you have to figure out where can the bromine go. So it could go, it's going to go to a benzylic position. So the benzylic positions that exist are here, here, or here. This benzylic position does not work because that's impossible, because it would break to octet if it were to go there. So it's going to go to either one of the other positions. Now this position is the most stable because it would be tertiary if it went there. Okay. All right. And I'm not sure, like, I need to know a little bit more about the specific questions that this person had. All right, so the next question they had is about deciding who is boss and how to kind of make sense of the activating and deactivating charts. So going to the activating and deactivating chart, do you guys know where that is? Can someone point me to like where I can find that quickly? I don't know which lecture it's in. January 26th.
I think it's from the 21st.
21st. Yeah, it's in a bunch of them too, though.
Yeah, the 21st, I think, is like the second page or the
Okay.
third, something like that.
Yeah, so definitely, so I opened up the 26th and I found it on page 9, and it's also probably on the 21st as well, within the first few pages. All right, so, okay. So basically, when I look at this chart, how am I going to make sense of it? So, you have to have the chart open while I'm talking though, because I'm not going to like write everything out. But first of all, take note of that the hydrogen. That hydrogen is going to be the standard of comparison. That's the line you draw between the activating ones and the deactivating ones. Let's start by looking at activating ones. So we start off with some different alkyl groups. So there's like carbon-hydrogen double bonds. There's just R, which is just any other alkyl without double bonds. And then there are the O's. So these two are O and then a carbon. Okay. The O, the benzene ring is going to be attached to an O and then a carbon. And then on top of that, there's the nitrogen ones. So one of the rules that I memorize is anytime a benzene ring attaches to an O, it's going to be activating. Because if you notice at the bottom, the strongly deactivating ones are all attached to a carbon and then a ketone or a carbon So like it's basically it's the difference between attaching to a carbon and the O is up here, or attaching to an oxygen and then the carbon is on the other side. Okay, so that's the difference. This is going to be activating. This is going to be deactivating. Okay, that's one of the differences you can notice. Nitrogens, in terms of nitrogens, anytime it attaches to a nitrogen, that's going to be strongly activating. Except for one position where it's the most deactivating thing ever. That's NO2. Very, very strongly deactivating. Okay, so those are some of the basic rules. Like you look at it and you see, oh, okay, like anytime it attaches to a carbon and then an oxygen, that's deactivating. Anytime it attaches to an oxygen and then anything else, if it attaches to an oxygen directly, that's why I'm going to change this actually. It's just anytime it attaches to an oxygen, period. Anytime we attach a benzoylic ring to an oxygen, it's very activating. Anytime we attach it to a nitrogen, it's extremely strongly activating, except for the case of NO2. And then all your ones with ketone, all the ones that are like attached to a carbon and then a ketone are very strongly deactivating. Halogens are just, the halogens are the most kind of weird thing about this chart. They are deactivating, but they're orthoparadirecting. So usually all your activating things are orthoparadirecting, all your deactivating things are metadirecting. But the halogen is the only exception where it's deactivating, very slightly deactivating, but orthoparadirecting, as if it was activating. Okay. So that's kind of how I make sense of the chart. And then when you look at it, when you have like a benzene ring, you have to figure out which one's the most activating. Then figure out where will that direct. Then, make your decision about what to do. Okay. And then the person asked, when you have a lone pair, they said, are these rules okay? These rules. So I want to say the rules, and then you guys tell me in the chat if you think it works or not, because I haven't really thought about it yet. When you have a lone pair, it's activating. Is that a rule that you can make? Hmm. This is actually fun. Okay, I'm getting a lot of mixed answers. So people are saying yes, people are saying no. When you have a lone pair, it's activating. I mean, I think that that's like a hard thing to say. Like if you look at this list, yes, the lone pairs are activating at the top. But I mean, there's lone pairs towards the end, and then yeah, Lakshmi, that's a really good point. She said halides have lone pairs and they're deactivating. And also, like if you look at the bottom, the very strongly deactivating, all the way at the bottom, the one that's sulfonic acid, that one has lone pairs. Um, so I don't like that blanket statement, but it works, I guess, if you understand the limitations of what you're saying. Um, when we have a C connected to an O or another thing that is strongly electronegative, it's deactivating. When we have a C that's connected to an O or something that's strongly electronegative, it's deactivating. That seems again, like I don't really like that rule because if you go up to the top of the list, I mean, the thing is that you understand what you're saying, So any rules you make up that you understand that the limitations of what you're saying, then that's okay. But for example, let's take this group. Is that not an O, a C attached to an O? And it's very activating. So instead, I like to think about what is my benzene ring directly attached to? If your benzene ring is directly attached to an O, it is definitely activating. If it's directly attached to a C, that is attached to a double bonded O, it is definitely deactivating. Okay? Um, do you guys have any other tips, like any rules that you remember? Any ways that you guys like to distinguish between activating and deactivating? Type it in the chat. Okay, and meanwhile, while you guys are thinking about that, I'm gonna head back to the exam because someone asked about question number 7 on the exam. Isn't question number 7 the big one though? The person who asked about question 7, do you want me to go over the whole of question 7? Or is there a specific one? Question A and B from question 7 on the exam. Okay. All right. So 7A. So 7A shows this. Okay. So basically, this is reacting with a strong base, OCH2, CH3. Again, like I said, anytime you see a sodium, just cross it out. It's in the spectator. So basically, what does that do? Like, that eliminates things. A base, it's going to eliminate the bromine. Where is the bromine going to go? Well, you have two options, right? This is something we talked about before. By the way, did someone talk to Dr. Son about that one question where I kind of disagreed on the location of the double bond? Because it didn't follow Zaitsev's rule? I feel like I don't remember where that was or anything, but if anyone asked him about it and has an answer, let me know. Okay. Okay, if you can send me like where it was, if you can remind me where it was and everything, then I can send him a quick email. Anyways, so where is our bromine gonna go? So here's our bromine. It's gonna protonate. It's gonna form a double bond with a beta hydrogen. Okay, we have a beta hydrogen here. We have a beta hydrogen here. Which beta hydrogen is gonna use? Carla, could you answer this?
Yeah, sorry, could you repeat that?
So there's two beta hydrogens, right? So which beta hydrogen is going to be used for the elimination in question 7A?
The one at the top?
Yes, exactly. Why?
Because it's closer to the benzene.
That, but also there's a specific word I'm looking for. Conjugation. Conjugation. Why? Because now we have that whole situation like it's really, really good. It's like double, single, double, single, double, single, double, single. Like it goes all the way around. You know what I mean? So it's pretty good, the conjugation there. Okay, so that's the main reason. Question B. All right, so there is a benzene ring and it is reacting with this. So this is going to be an alkylation. Okay, so for this alkylation, he says rearrangement beforehand, which is like really, really good of him because people would mess up on this a lot more if he didn't mention it. Okay, so for this rearrangement situation, so we're doing alkylation. So you have to remember what happens. So one of the first things is that this Cl protonates, okay? So that means we're left with this. But what's going to happen? In the chat, what's going to happen? This is our type of rearrangement. Good. So some people are saying methyl shift, but it's actually going to be a hydride shift. So a methyl shift would help, but the most stable thing would actually be a hydride shift. Okay, let's review this a little bit bigger. So basically, there's a positive charge here. If I was going to do a methyl shift, that works. So basically, moving that methyl, we get, now this is in a secondary position. So from primary to secondary. But how about a hydride shift? If we did a hydride shift, that would give us a tertiary carbocation. So that's actually what's going to happen, more likely. So then the tertiary carbocation is just going to attack it. So I'm going to rearrange this. Positive charge here. Positive charge is going to attack there. We get this with the tertiary carbocation attacked it. Questions? Okay. People are saying 7M on the exam was the one that... Okay. Has anyone been able to figure out like a solution to that? Or no? I still don't see why. Like, it doesn't make any sense. I think that was a mistake, but I'm gonna email him that. Okay, I also just wanted to get back to that email real quick, which I had nearly finished. But there was a couple of things left over. So chapter 12 review number 4. Chapter 12 review. I'm not sure I know where to find that. Do you guys have any tips? Chapter 12. Okay, I found a chapter 12 on January 21st, so it's kind of towards the beginning. There's the review. Okay, I think I found it. Okay, this is a little bit weird. Okay, so JD's saying there's more than one review. Yeah, that's a good question. The person who asked isn't here, but I'll open up all the reviews and I guess do all the number 4s. I don't know. Also, guys, feel free to talk because there's not that many people here today. 12 people, so you guys can open your mics if you want, if that's more comfortable for you.
January 26th has one chapter 12. The number 4 looks kind of difficult, so.
Okay, yeah, I think that's the one they were asking about because they were asking about activating and deactivating groups. So let's just do this one. So the 26th has a chapter 12 review, and this is what it looks like. I'm kind of drawing in like a little bit of different orientation, but just ignore. Okay, so basically the question here is which kind of this is a bromination. So it's reacting with Br2, Fe, Br3. Okay, so we have to figure out, is it going to go to this benzene ring or this benzene ring? So if you look at that list, right? If you look at that list, all of the extremely deactivating ones attach to the carbon and then the oxygen. All the activating ones attach to the oxygen first. So we want to attack the side that is attached to the oxygen first because this is activating on that side. On the other side, it's extremely deactivating because it attaches to carbon, then oxygen. So we know that's going to do bromination there. Now, the other thing is that since it's activating, it's also ortho-para-directing. So we're going to have to put it in either the ortho position or the para position. Okay? So what's the ortho position right here? Para position is right here. But which one is going to win? The para position is going to win because the stereo hindrance, this is not a small group, you know. So just to reiterate, which one is boss? This one is boss. Ooh, my pencil just died again. The one on the left is boss because it's the O and then the C. It's very activating. The other one is very strongly deactivating. So we don't want to put it there. Okay. And I think that might be the end of their questions. Okay. And then also just to answer the last question, your exam will be like the quiz. You print it off, you have a certain amount of time to finish it. You have a little extra time so that you can scan it and email it or upload it to SKCT. I think he definitely prefers it if you can upload it to SKCT. That's better. One thing that I do is I use my cam scanner and I email it to myself. Then I get on my laptop real quick because it's such a pain on my phone to like upload things to SKCT. So I email it to myself from the cam scanner. I get on my computer real quick, download it onto my laptop, upload it onto SKCT. Um, so it seems like a lot, but it actually only takes like 2 minutes. Okay, yeah, JD's saying she does the exact same thing. My tip is just go for the laptop. The laptop is easier for actually uploading it. Does anyone else have any tips about submitting your quizzes and exams?
Cam Scanner has different functions, so depending on um, how good your handwriting is and how dark your marks are, you can set it so that, yeah, um, you can set it so that there's like a black and white version. There's like, I
Hmm.
think, there's a couple different like what's it called? I guess it's called filters, maybe they're filters, but
Hmm.
some of them like greatly increase the legibility of your handwriting. So
Yeah.
even if it's like low resolution, the other thing which is maybe like not so recommended is if you do it in pen, the markings are really crisp and really clear compared to pencil.
Hmm.
Um, but that also requires you to have like the incredible confidence
Yeah.
and ability to do organic chemistry in pens. So maybe
Yeah.
that's not something you want to do. If you have a printer, print, because drawing the stuff out means that there are two opportunities for you to count your carbons wrong.
Yeah, for sure. Oh, and Aishan is saying, because this is probably only if you have an iPhone though. I do not have an iPhone, but Aisha is saying to airdrop your cam scanner file to your laptop if you have the like a MacBook and an iPhone. So that would be like really good. I mean, I have to email it to myself.
I
It doesn't even take, again, it just takes 2 minutes
yeah,
to email it to myself and upload it. But if you can airdrop it, that's even faster, I think.
actually
Also,
do it
Bluetooth.
every
Hmm?
time every time I try to like airdrop or email, it
Hmm.
gives me like whole text that says it's an encrypted file and won't actually let me like.
Ooh,
So I like have to like upload it onto either like my Google account or I just log into my computer or cam scanner. Sometimes it takes a little while for like it to upload
oh,
cloud, and then I download it that way.
oh God, that actually seems like a pain. So that, how long does that take you?
I mean, uploading it to the thing, it maybe takes me about 5 minutes. Doesn't take that long.
Ooh,
But when
that's
like
a lot though.
I'm freaking out trying to like do it, sometimes it doesn't pair up that quickly and it takes forever.
Yeah, that's really crazy about like the encryption thing. I never get that, so I don't know. But maybe you could consider using a different scanner then. If you test it out and see like does the thing not come into encrypted, that might be better because that's a long time. Like I usually only spend 2 minutes uploading my stuff once I'm done. Oh, one last tip I have. So Persa also says to Bluetooth works. I don't even know if I know how to Bluetooth a document to my computer. But if you know how to do that, then that seems also like a really quick solution. But the last tip that I have is use your flash when you're taking your pictures with Cam Scanner. I don't know about the other scanning apps, but like use your flash. It makes it so much better. Um, like I don't know why, it just like it focuses on the page so much better if you use flash. So definitely test that out and see if it works well for you. Sometimes, like with certain lighting conditions, it will make your page look shiny, but like rarely. Like for me, it usually works so well if I use Flash. Um, okay. So, and then again, like if you have an iPad, you can just draw straight onto your iPad and submit it like that. Submit a digital thing. But ever since I started doing that, Dr. San didn't like it. Like he couldn't use my answers and like the answer keys because I don't know, like it just looked really bad when I uploaded it again. I don't know how to describe it, but the format was way off because like my Notability app messes up the format of the exam, so it doesn't really work that well. So only do that if he doesn't really rely on any one person for their answer keys in this class, but when I was doing it, we were like 4 people in the class, so. All right. Uh, can we go over 5F, 6A, and 6D? So this is, I'm assuming, from the exam. Oh, I got some more questions too. Okay. Let's start with, oh, from the February 4th notes. Okay. Everyone go to February 4th notes. We're going to be doing some questions from there, and then we're going to move back to the exam. Okay. February 4th class notes. Oh yeah, I told you guys to go over this last time we spoke because I didn't really have enough time to go over all of it. Okay, 5F. Okay. So February 4th again, 5F. So what this is, it looks like that. And this is reacting with, I'm just going to change it real quick. Okay. All right. So, all right. So what's this going to do? Okay. I don't know. I'm thinking, is there an answer key for this? Let me see. Oh, there is. Okay. Yeah. Okay, well, I guess my question is, it's not as MGBR yet. Oh, well, it just has to be a good leaving group. Okay. So, what's that? That thing inside the bracket, you just take that out and put a negative charge on it, basically. Right? That's the nucleophile. So, what do nucleophiles do? They do substitution. So, what is substitution? Substitution is taking something away and putting something else in its place. Right? So, bromine will protonate, and this will come attack the same spot. That's it. That's what substitution is. So, what are you going to get? You're going to get the same thing as before, but now we've attached a propyl to it. So we need to make sure that we've attached 3 additional carbons. So that's 1, 2, 3. So that's perfect. I think that's the right answer. Yeah. Okay. Next. And if something I'm saying isn't that clear, just let me know. 6A and 6D. All right, 6A. Oh, I like these ones. All right, so for 6A, we have a carbonyl group. All right, so this one is reacting with excess of this, the triangle. It's like so cool. And H3O+. The H3O+ isn't really relevant here. It's just the solvent that you need. So, what we're gonna do is, again, it's like the same thing. So this is just a negative charge on the triangle. So this triangle is gonna attack the carbon right there. The first thing that's gonna happen is what? What happens when the triangle attacks there? It's gonna break octet. So what's the thing that's gonna resolve that octet issue? And for anyone confused about what am I saying when I say break octet, basically I mean that here's a carbon. If I were to attach that to the triangle as well, this carbon is now attached to 5 different things. It has 5 valence electrons. That is not good. Carbons should only ever be attached to 4 things. Or if it has like a negative charge, it'll be attached to 3 things. Yes, so what's going to happen is that this ester is going to break. So I did that in a red line. Ester breaks off. So what we get after the first time, he said excess, but let's, go one by one. So the first time that it does, it's going to look like this. So we've broken off that ester, and the triangle is now there. Next, another triangle is going to attack. I feel like I should stop calling these triangles. That feels disrespectful to orgo. So what's this going to do? Okay, so that's just going to attach another triangle on, and this becomes an OH. Exactly. You guys all got it right. All right, so that's question 6A. Is that good? Good explanation or? Okay. 6D. 6D. All right, so this is one of the ones that like you have to is this one going to be on the exam? I'm not sure if this one's on the exam. Do you guys know? It's going to be on the exam? Okay. All right. So in this situation, we're reacting this with All right. So what's the situation here? So I guess from what I'm seeing, I don't really remember this solvent, to be honest. But I would say that anytime I see something that I don't remember, I just look at what it does and take that as the rule, you know? So what has it done here? It took the double bond and turned it into a triangle between, like, there's some important things to note here. So, like, again, like, guys, I don't even remember what this is, but look, it's going where the double bond was, it forms a triangle between those two carbons where the double bond was. And this is not like, this is not like epoxidation. So in epoxidation, you have a double bond and you do whatever epoxidation, and now you get a double bond with an oxygen between. No, this is another carbon being added, right? That must have come from here. There's a CH2 right there. And JD's saying this is Simmons-Smith reaction.
Yeah, it's the Simmons-Smith reaction. And the other thing about that reaction that's really weird is like it's not relevant here because this is a cyclohexane, but in question number 8 on our exam review problems, like the additional exam review problems, not like the exam, whatever is attached to the ends of that triangle becomes cis.
Okay, so let's say that I had a chain before with a double bond here. No. Let's say, okay, never mind. Let's say that I
No, that was fine what you drew before.
Okay, all right. So let's say that I had this with a double bond here. I mean, it's already, oh, okay, yeah, it's trans. Okay, so if I reacted this with whatever, CH2I2 zinc, like, I don't know why this is complete, like, I don't remember this at all. I don't think anyone's brought it up this semester so far. So basically, you just form your double bond, but basically, you form your triangle, right? Remember, it's not the epoxidation triangle. And then this is going to be, they're going to be cis to each other, each side. Okay? Yeah. So that's the answer. So you need to make sure that both of the carbons coming right off of it, like right here, they need to be pointing in the same direction. That's what cis means. So they're both pointing down. Whereas before, on the double bond, one had been pointing in this direction, the other had been pointing in this direction. In the end, they're cis. They're pointing in the same direction. So that's a really good point, yeah. Oh yeah, I just saw another one too. Okay. So yeah, this one you definitely need to know. I just saw one on the exam as well. Okay, the next thing, so thanks for bringing that up, Carla, because that was a really good question that I'm glad we were able to talk about because I haven't gone over that at all this semester. Okay, so someone said, can I go over question 11 and question 12 from the exam? So let's just transition back to the exam real quick. Question 11, question 12. Okay, so question 11 says that there's a nitration of a chlorobenzene. Now, what is chlorobenzene? I'm thinking it's a benzene ring with a chlorine on it. That's it. So we're doing nitration of this, and it has a reaction rate that is blank than the reaction rate of benzene, which is regular benzene, right? So, is the reaction of nitrating a benzene with a chlorine faster or slower than nitration of the regular benzene? Which one reacts faster? Let me see. Anthe?
Um, I think it's the one without the chlorine, because like does the chlorine substitute like make it slower?
See, exactly. You're correct. You're 100% correct. This is deactivating, which a lot of people forget, let me tell you. So chlorine is deactivating. So it's actually going to react slower than the plain benzene. So you would say the reaction rate of the chlorobenzene is slower than the nitration of a regular benzene, and it gives primarily what? Orthopara or meta?
I believe orthopara, right?
Exactly. Chlorine, the halides are those weird groups. They're orthopara directing, but they're also deactivating. Watch out
Mhm.
for them. Make sure you remember. All right, good job, guys. Let's do the next one. So someone said, oh, so also question 12. Yeah, these are the questions. Wow, that question was a surprise to me. Um, but like you can try to figure these things out on exams and you'll be fine. So, which point on the potential energy diagram corresponds to the species shown on the right for the electrophilic bromination of benzene? Okay, so wait, which point on the potential energy diagram? Okay, so we're at the spot here where, okay, so we have, all right, so we have something with a bromine on it, and it's clearly something is happening to it. Right here, what's happening is actually bromination. So bromination is occurring. This is one of the steps that occurs between it. And kind of the next step is the hydrogen coming down to form the double bond, and now bromination is over. So basically, it's asking which step correlates to this. So kind of what I was thinking is, okay, clearly it's not D. So this is, let me do another thing here. All right. So D is all the way down here. It's clearly not D. So it'll be either A, B, or C. But look at this. Um, the state of A and B are going to be things that are, I don't know how to explain that. The peaks of your energy diagrams are usually positions that are after accomplishing something. So we have a carbocation, then we form a double bond. You know what I mean? It's like a step where something hard has to happen. So a peak is a step where something hard has to happen. So this would be considered a lower energy step. The next step, which is probably step C, is a step that would look like this. It would look like hydrogen getting away and these double bonds coming down, the lone pairs. This is more like what C would be. Does that give you a sense for like what the peaks on energy diagrams mean?
Yeah, thank you.
Yeah, no problem. So if there's a peak, that means it's a really hard step to get over. It's like a hump that you have to try to get over. But a more resting state, which is like a dip, would be a position where it's just sitting like this and it has nothing going on. Nothing's being put on, nothing's being taken away. All right. And it's not D because D would be your end product. All right. So someone said that they have a question. Oh, okay. We have so many questions. Um, let me just go back. I'm gonna try to answer these in order. Can we go over making alcohol with a Grignard, especially on what makes a primary versus secondary versus a tertiary carbon? Okay. So I'm not sure about like what you're saying about primary versus secondary versus tertiary carbon, but I do understand what you're saying about an alcohol. How do we create alcohols with Grignard? So it's kind of simple. With Grignards, we have double bonds, double bonded oxygens, and they will be attached to something, right? Let's say R and R prime. What we do is, oh, and okay, the difference between primary versus secondary versus tertiary alcohols. Okay, well, I will say though that, I mean, okay, yeah, that's a good point. That is a really good point, guys. When you're doing your retrosynthesis, you're gonna want to have to know how to form a primary versus secondary versus tertiary alcohol. And let me give you an example. Let's say that I had a retrosynthesis that ended up like this. Okay, so that's a primary alcohol, right? How could we have gotten here? I'm gonna rephrase these questions a little bit. How could we have gotten here? We could have gotten here from our double bonded oxygen being like this. That is necessary, and I'll talk to you a little bit about why. And also, our other group was like this. All right. So this is a really, really good point. I'm so glad you brought this up because this is a really good thing to talk about. So, basically, what do we have here? How did I know that this was exactly what it must have been before and this is what it must have been? Because it's kind of just from, this is actually a little hard, I'm not gonna lie, to explain how to know that. But it's kind of like from knowing that, gosh, I don't know how to say this. Does anyone want to step in and like explain? I don't know how to like explain knowing that like um that this was definitely COH2.
I
It kind
mean,
of hmm
you kind of just have to memorize it, right? Because
I wouldn't say memorize it. I definitely wouldn't say memorize it.
no, because like if it's primary, then it has to be like COH2. Like if it's a primary alcohol, it
Okay,
has
yeah.
to.
I have a way of putting this. Okay, so you could definitely memorize, yeah, you could definitely memorize it, and that wouldn't be the worst thing. But let's put it this way. Yeah, that's a really good point, Julie. So this O is only attached to one carbon. That means it could have never been attached to another carbon. If we have an O that's attached to a carbon, then never mind. um, yeah, I mean, no. Yes. Because, okay, so what does alcohol mean? So a primary, let's actually first define what's an alcohol. What's a primary alcohol versus a secondary alcohol? Okay, so yeah, this is actually a really good first step. Because what is a primary versus a secondary versus a tertiary alcohol? So basically, a primary, so all alcohols are only attached to one carbon, right? There's no such thing as an alcohol attached to more than one carbon, right? So really, what defines whether it's primary, secondary, tertiary is how many carbons that carbon is attached to. Do you guys get that? So in this case, that carbon that's adjacent to the OH is attached to one carbon. That carbon is attached to two carbons. That carbon is attached to three carbons. Do we get that? What's the definition of primary, secondary, tertiary alcohols? It's a little different. It's a little different than, carbons or carbocations. You know what I mean? Okay. So now that we got that out of the way, when we have a primary carbon, a primary alcohol, that carbon, see the O is attached to one carbon, that carbon must have not been attached to any other carbons. Okay, that's the example I wrote above. Now, when we have a secondary carbon, that carbon must have been attached to one carbon and another hydrogen, right? If we have a tertiary carbon, tertiary alcohol, that ketone must have been attached to two carbons. Okay, I guess this seems like something you can memorize then. Okay, so it kind of like increases by one carbon every time you do a Grignard. Does that make sense? I'm so glad we're talking about this. I'm having like an epiphany right now. Because I always just did it and didn't really like think about any patterns there. So basically, every time you do a Grignard, you're adding one more to that alcohol. So this alcohol went from, that's not even primary, you know, it's just a carbon. So then it goes to being primary. Goes from primary to secondary, goes from secondary to tertiary. Okay, does that work? And then knowing the mechanism of Grignard is also just another way of doing this. Like just knowing the way that Grignard works. Okay. Do you want me to explain more about Grignard? Is this enough? Because I don't want to explain if like everyone knows what I'm talking about. Okay, perfect. All right, I'm just going to continue going through the questions real quick. Someone said, can I go over question 10? Question 10 from the exam. Okay. So question 10. Okay. Sorry, just a minute. Oh, these are not all the same. That is so ugly. I'm sorry, guys. Okay. All right, so it says all hydrocarbons are very weak acids. However, one of them is far more acidic than the other. Which one is the strongest acid? Okay, so this is a question about aromaticity. So I said that, what's the definition of an acid? An acid is something that wants to give up its hydrogens, right? Acid is something that wants to give its hydrogen. So if it would only want to give up its hydrogens if that creates a more stable molecule. All right. So we need to see which of these, by losing a hydrogen, becomes even more stable. And as we know, aromatic is the most stable thing. So ideally, we're looking for something that when it loses a hydrogen, it becomes aromatic. That would be like a pretty good acid. So, looking at this one, like the first one, let's say we took away, there's two hydrogens to take, right? You could take this hydrogen or you could take this hydrogen. So, I mean, let's just say I take one of them, gone. Now we have a lone pair here, which is a negative charge. So if we kind of count up all of our, well, first of all, I mean, this isn't even conjugated. Look, there's like, it's not conjugated the whole way. So that really does take it off the table. There's no need to investigate farther. Second one, if we take, there's this hydrogen to lose. So I'm going to erase it. We take it away. Now it's a negative charge. And that is actually, looks like it's going to be aromatic. Number one, it's conjugated all the way through. Number two, it has 1, 2, 3, 4, 5. So it has 10. Oops. It has 10 pi electrons, which fits our thing. So that would be 4 times n. Oops. That would be 4 times n plus 2, and n is simply 2. So that's 8 plus 2, which is 10. So that fits our formula, 4n plus 2. It's not a multiple of 4, so it works. And then, so this one becomes aromatic afterwards. So that would indicate that it's very acidic. Not very acidic, very weak acid that's far stronger than the others. And then over here, we have a hydrogen to lose from this position. If I take that hydrogen away, the issue here is that it actually does match with our 4N. So we have 3 here, so that's 6 altogether, so 12 pi electrons. 12 pi electrons is 4 times 3. So it doesn't work. There's no +2. Is that good? For the person who asked? Okay. Someone said they have a question relating to 11. Carla, do you want to go ahead and say what that question is?
Yeah, I was just wondering for what we were talking about, is it the more strongly activating the like faster the reaction?
Yes, that is correct.
Okay, that was it. Thank you.
So yeah, when something is more activating, it's much more likely to happen spontaneously without the need for any like catalysts or anything. All right. Okay, I don't have any other questions at this point. Did you guys go through everything? Like, how are you feeling about your prep? Is there anything you haven't gone through yet that you would want me to go through? Like, even if you don't have specific questions about it, you're like, I'm behind on that. Bonus C. Oh my God, yeah. I think he completely butchered me there. Oh no, oh my God, yeah, okay. Let me give it a second attempt without looking at the key. Ooh, this one's not easy. Not really. Um, okay. So, um, all right. So clearly, the first thing is when you look at this, there's no way we can attach this on without it having been, what do you call it? What do you call that first? Like an acylation or whatever? Yeah, acylation. So it must have had a ketone on it, is what I'm trying to say. I don't know if I'm using the right word. Um, so that one, because that would have had a rearrangement. The double bond, it could have come from pronation of a Br or a protonation of OH, but definitely I'm gonna go with the protonation of a Br. So, um, meta. Okay, so I have an idea, but I'm just gonna. This one's actually pretty complicated, which is why it's bonus. Um, okay. So, let's see that first. Okay, first let's take our regular thing and attach the methyl. Yeah, that would be the best. Yeah, that's definitely the best. Okay, okay, so if we take this and attach the methyl first, then wait, he gave 4 points for this question, but then redid the whole thing. 4 out of 5. Okay, we'll look into it in a minute about like the details of what steps come first. But definitely, in retrospect, this is a better approach to add the methyl first. So if we add the methyl first, that's really great because it will help this get into the para position and it will help this get into the ortho position. So it's kind of ingenious. So next, we're going to let's put on the para position one first because that'll help that other one get into the exact right position. So I'll just go like here. Wait. Okay, so that's one too many. All right, so this, and we'll get that into position. All right, and then from here, so that went to the para position. Now we can, if we put in our ethyl, it'll be perfect because it'll kind of add it in without um, with it going to the exact right position, because this will drag it towards the ortho position and this will drag it towards the meta position, so it'll be perfect. So there we go with that. Then we're going to need to do MBS because we need to get like a bromine on here so that we can eliminate it. So MBS. Okay. After our MBS, we're going to have to eliminate it. You guys can probably see the steps from here on. So we're going to have to eliminate the bromine, then we're going to have to take care of that ketone, and then we're done. That's it. Okay, so what are some other options for doing this? So so these are the steps that they did first. So just to put it out in that kind of flat orientation that I like to do sometimes, first he added the methyl, then he added that thing, then he did, finally, what did he do? Then he did the other thing. Okay. All right. So that's the steps that Dr. Song likes the best, which would probably earn you 5 points. The steps that that I had ended up doing was first I did the this one, then I added, doesn't really make a lot of sense, but it works. So then I added this, and then I added the methyl. So what's the problem with this option? There's nothing wrong with it per se, but there is something worse about it than the above reaction. What's the problem with adding that one first? Why does this not get full points? Good job. Good job, yeah. I have one correct answer so far. Oh, you guys don't? Okay. All right, so it seems like a lot of people really don't know, but it's basically because this is really deactivating. That's a huge deactivating step. Our yield for this thing would be so low. Remember the difference in numbers? When you have a very activating thing in a benzene ring, it can be like if we have one something that's very activating. Actually, let me change this to A. So if I had something that was very activating versus something that was very deactivating, the activating thing would be like 75, and the deactivating thing would be like 4.2 times 10 to the negative 5. Can you imagine the difference in yield here? This reaction is way better. Like, infinitely better. So look at the difference of numbers right there. So that's why he said, no, this does not get full points, because it's not the smartest solution. It's a solution that technically works, but it's going to be very bad, very low yield. Okay, does anyone have any other suggestions for ways to do this? Because there's always multiple ways. Some of them are not going to be perfect, but they're still good to think about. Okay. All right, you guys seem good with this then.
Wait, I have just a quick question. When we have like synthesis problems like that, should we try to always add like the activating ones first and then go to the deactivating ones?
Yes, absolutely. Sometimes it won't work so well because of the directing aspect,
Mhm.
which is the other thing. Like those are the two major things you need to juggle, which is why these questions are a little bit tough. You need to juggle the idea of where is it directing versus how much is it activating. But if you have the option between two starting points that both get you to the endpoint, choose the one that's more activating.
Okay.
But the first most important thing is to make sure that it directs to the proper position. That's actually more important than how much it activates. Because like we want the right answer. Now, sometimes there's a way to make it with a higher yield, but even if it has a lower yield, you need to write the right answer. Someone bromin someone brominated and made a grignard. That's very creative. That's very creative, gotta say. Um, then you probably have to like eliminate the oxygen. I did think about that. I really did. I was like, oh, that double. So I thought to myself for a second, I was like, hey, this double bond right here, this could have come from the elimination of an oxygen, an alcohol, which could have been from a Grignard. But that's just like so many steps. Oh my God, someone else did that too. That's hilarious. That would be such a long retrosynthesis. It would be wild. So yeah, it's better to just do a MBS. All right, how are you guys feeling about naming? That's like one of the things that's like I'm always like outside of the chem door, like memorizing that real quick before I go in. Yeah. So can we go over that? So I'll do a mini quiz for you guys. Um, I'll do functional groups. So and then we can try some actual names. So what's this group? One answer only. This is the easy one. Wait, really? No one? There's only one answer. This is funny. Okay. Okay, finally, yes, phenol. Phenol. Is naming a big part of the exam? It'll just be a couple of questions, yes. It'll only be a few questions. But sometimes he throws it in a sneaky way to another question. Like where it's like, oh, this weird name reacts with this weird name. So then you have to kind of know. So this one is phenol. I don't know how to explain knowing that one. It's kind of in the name, all, right? OL stands for alcohol. So that's phenol. Okay. Yeah, phenyl. Phenyl is basically this ring, like a benzene ring. That's what a phenyl is. So it's a phenyl and an alcohol. So the OL is for the alcohol. All right, this one. I'm starting with the easy ones, guys. There's only 7 you need to know. 2 answers so far. 3 answers. 4 answers. No, still 3 answers. It, maybe you guys didn't, study this yet. I mean, I'm not gonna lie, this is something that I usually memorize right while I'm outside. Oh, Toluene, I have no idea how to spell it. Yes. You do not need to know how to spell. Thank God. Or else I'd fail. Um, yeah, so this is Toluene. So Toluene is let me tell you something about Toluene. I recently heard that people get high sniffing it. So I don't know if that will help you remember it. I was just watching a video and they were like, these kids in this poor area sniff Toluene, and I was like, I know what that is. I could draw that for you right now. I got so excited. Okay. Next. What's this? This is the one that I don't really like so much. Yeah, aniline. I really, guys, from the bottom of my heart, I have a grudge towards nitrogen. Like, it is the worst. The worst, guys. Okay. So, aniline. Yeah. And then we have, okay, what's that? Yes. Okay. So some memorization tips now that we finished the four. No, no, there's one more. What's that? Styrene. Okay, so some tips for the 5 easy ones, and then there's going to be 3 harder ones after that. So, so phenol we already discussed. It's the all just alcohol, whatever. Phenyl is the benzene ring. Toluene, just remember like the high joke, and styrene is ene. Ene stands for double bond, so styrene. Um, Now between anisole and aniline, JD had a really, really good tip. She said, because like anisole has an O in it, and aniline has an N at the end of it. So, anisole has an O, aniline has an N. So that's the one that's an O and then a methyl, and aniline is the one that's NH2. Also, she says for styrene, she said styrene polymers make styrofoam, which is kind of fun too. Okay, and then for the other ones, there is 3. There's this one, which I think is the easiest out of the 3 of them. There's this one, and there is. Okay, so between these 3, this one is the easy one to recognize. It's benzoic acid. Benzoic from benzene. And acid because this is an acid complex. It's resonance here. So if I give up the hydrogen, then I'm going to have negatively charged oxygen here, and there's going to be a ton of resonance happening, or not that way, really. um, I keep drawing my resonance the wrong way. It's going to be more like this. The lone pair is coming up and down. It's going to be switching back and forth constantly. So, and we know that resonance leads to acidity. So this is benzoic acid. Then we have the 2 other ones. So this one is also easy because this is a benzaldehyde. And what's the significance of benzaldehyde? Well, aldehyde is simply a ketone that has a hydrogen on one side and something else on the other. That's what an aldehyde is. Okay. So that's benzaldehyde. The last one, really, I don't really understand. Like it just breaks the whole benz thing, and it's acetophenone. So it's kind of like the odd man out. All right. So that's that for naming. Now let's go on to an actual naming question. So I'm just gonna take an example from the exam because I can't be bothered to find another one unless you guys have one for me. But let's do this first one. So this is question 1. So, all right. So when looking at this, this should scream, oh my God, that's one of my functional groups. That one is the acetophenone one. Or sorry, no, that's the benzaldehyde. So this one would be called a benzaldehyde. Okay. And also it has a chloro on it. So I'm going to call it a chlorobenzaldehyde. And they are in a meta position to each other. So just put an M before. So the name of the entire common name goes at the very end. Then you put anything else, whether it's nitro, chloro, bromo, fluoro. What else? What are some other options that could go there? These are pretty much the only ones he's going to give you. I don't think he'll even give you fluoro. And then the orientation to each other goes first. So, and he won't give you anything complicated with like 5 things coming off of it now. Second one, like here's the thing for those of you guys who are nervous and it's your first exam with Dr. San, he does not surprise you. If you go through and look at a whole bunch of naming questions from your notes, you will get the naming question right. He doesn't surprise you with like, oh my god, now I'm suddenly giving you 3 and I'm expecting you to know. So this one has, okay. So for this one, like, what is that? What is this? Oh, JD is saying cyano. Cyano is basically CN. Fluoro is just F. Bromo is Br. Chloro Cl, and nitro is NO2. Okay. So looking back at this one now, what is the common name that we know of? Out of the 8 that we memorized, what's the common name that works here? Anisole. All right. What do we put right before the anisole to describe the other group, the other functional group? Nitro. And what do we put right before that to describe the orientation? Ortho. Okay, perfect. So that's it. That's it to naming, and you should look at some more examples that you have if you have time, if you care for that kind of stuff. But yeah, it's not going to be a big deal in the exam, but it's definitely good to get, what is it, 4 points? Yeah, I mean, that's something, you know. That really is. That's half, because the exam is out of 100 points, so that's almost half a letter grade. So it really is no joke to be losing points on something like that. Especially when it's kind of easy to just like, look it up real quick before you go into the exam. And you guys already memorized it a good amount. Okay, any other questions? Is there partial credit? Yes, absolutely. If you look through that exam right there, he will be just as good with the grading. So for example, like if you looked at the bonus question, this is the perk about Dr. San. Look at that last page. It says bonus problems, 12 points, all or nothing. The first time I took his exam, I was so stressed. I was like, oh my God, it's all or nothing. That means I'm probably not going to get it because they're so hard. But then look, he gave partial credit on the last one. He always gives partial credit on the extra credit. I don't know why it says all or nothing. Um, he's very big into partial credit. He wants people to succeed. So if you go through the exam, you will see points where someone got, like on page 5, someone got question 10 wrong. He gave them 1 out of 4 points for not explaining at all. So if he underlines something, definitely pay attention to that underline and bolden part. He said explain, and like the person didn't really explain. He likes words a little bit, so sometimes he'll be like random like that. But the extra credit is a big part, so definitely if there's something you don't know, just write down stuff you do know about the topic. And Aishin's saying he gives you points for trying. Absolutely. He does. He gives you points for trying. He gives you points for showing that you understand something, or that you have some creativity in you if you don't remember anything. He's also been known to give extra credit for drawing a cow on your exam. But that was a long time ago, and he's learned his lesson, so now he doesn't do that anymore. Okay, any other questions? Yeah, the cow. Dr. San is obsessed with cows. They're his favorite animal. So if you want to get him a present or something, cows are a good way to go.
One thing that I found really useful is like if I look at a reaction and I know, for example, like it's a dehydration reaction, an alkylation reaction, a halogenation reaction. Even if I get like every other part of the question wrong, and as long as I can write like what kind of reaction it is, like
Oh, yeah.
that's yeah. It happened to me in exam 2 in Orgo 1 where I just got like a question like so wrong, but I knew it was like SN2 and he gave me partial credit.
Yeah. Oh, Melissa's saying that she sent a picture to Dr. San of her dog, her with her dog, because her dog was like a cow. That is so cute. Oh my God. I don't know if any of you guys know, but Dr. San, like across from his office, there's this room, and it's like full of like Dr. San memes, Dr. San cow stuff. Like it's amazing. It's amazing. Next time you're at Avery Point, go check it out. The room right across from his office has like a wall that's like covered with memes that they made about like his Orgo. It's all from his Orgo students because like no one enjoys Gen Chem. So it's all from his Orgo students and like it's all like quotes from his Orgo thing. Like they make jokes about like the way that like his sayings and stuff like that. Yeah, you have to visit Avery Point. You have to see this room. I was dying. I took pictures of everything. I don't know if I still have the pictures. If I do, I'll send them because you guys need to see it. It was adorable. Like I don't know if, like how he is with online classes, but like the just the you know just the sayings and stuff and like the cows, like there's a whole shelf like full of cow gifts that people gave him. He doesn't really take them home, he just puts them on the shelf. Yes, you should print off a picture of your dog and put it on the wall. Yeah, this all started because someone a few years ago, I don't know, like I heard like maybe like 5 to 7 years ago, someone drew a cow on their exam and he gave them 1 point extra. And ever since then, people have been trying, but he's never done it again. Oh, someone had another question. Okay. Question 2, 8, and 9 on the exam. Okay. Question 2, we have to go through this quick because we have 3 more minutes. No, we have till 9:20. Never mind. Okay. So question 2, um, all right. We have 4 benzene rings. One of them is a bromo. One of them is a nitro. One of them is anisole. And one of them is just plain benzene. So it says rank them from increasing reactivity to nitration. So when we're going to be nitrating them, which means, substituting an NO2 onto it, we have to figure out like which ones are going to be the most activating, blah, 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 blah. So what's the most activating thing here? That would by far be this one. So I'm going to number these 1, 2. I'm just going to rearrange. I'm going to rearrange them with my thing. Okay, so here's 1. This is by far the most activating thing. The next most activating thing is this. Then the bromine, then the NO2. Does that make sense? I know I just told you what the answer key already says, but I mean, it has to do with activation. Okay. Question 8. Okay, question 8. We have do the synthesis below. Okay, this one's gonna be fun. Okay, so a little bit more space here, but this is reacting with Et2O, which is really important. So we're gonna form one product here, then we're gonna react that with firstly, and also H3O+. Okay, whatever. So now we just need to figure out what goes in each of those boxes. So the first thing that's going to happen is because of the not because of the ET2O, because of the presence of this hydrogen right here, it's going to be kind of like an acid-base reaction. So this hydrogen is going to go onto there, and this MgBr is going to come onto the carbon. So what we get is we get this. That's the first step. And that's just what happens when you have that triple bonded carbon, because that triple bonded carbon would way prefer to have the MgBr on it. So this is the first step, which goes in here. Gosh, that's so small. Then after that, can you guys still see it on the screen? Kind of. So then after that, it's reacting with a strong base. But no, that's not a strong base. I read it completely wrongly. Oh my god. I read it as a base, but it's actually not at all. That is to convert it to bond line structure. It's going to look like this. Okay, that's what it is. So this is just a Grignard. So what's going to happen is I'm just going to draw the, so when the, I'm just going to draw this top part. So the OH now, the ketone became an OH because it attacked from the other side. And what happens is that this is going to be like that. Okay. So basically, in other words, this triple bonded carbon part came along with its negative charge and attacked the underside of this, the carbonyl. So that went up, became an OH. So that's how that one works. Question 9.
Oh, wait, I have a question about that one. Why do we have the methyl coming out after like the OH, the one that's like lingering at the outside?
Oh, this one?
Yeah, that one.
Yeah, that is just, let me get my red out. Here. It's this methyl.
Oh, okay.
I'm sorry for the flip and like the orientation flip, but that's basically what it is.
Okay, thank you.
Okay, 9. So for 9, he has 9A, and 9A is okay. So what kind of Grignard reagents were used to a Grignard reagent and a carbonyl compound? Which are the two things that contributed to this? So this is one of those ones. So I would use the rule that we found out earlier. That was actually like kind of surprising to me that we discovered that. But look, this is here's the carbon that the oxygen is attached to, and then that is tertiary. So that means that our reaction, the carbonyl was secondary, right? So that means it was attached to a carbon and a carbon. Now the two carbons it was attached to, like by the way, there's multiple ways of doing this. There really are, oops, sorry. There really are multiple ways of doing this. So just do which one you prefer. So I'm just gonna make the assumption that these were like this. and that the Grignard reagent was like this. That's the way that I prefer to think about it. But you really could do anything. Um, it's kind of hard for me to explain this one, like if I can't really get you to like, um, Carla, did you have a different solution maybe? Because there are lots of ways you could do this. So I'll
Um,
show you, uh-huh.
yeah, not right now.
Okay, so there's multiple ways you could do this. So this would be like one way. Another way would be to say that it came from the ketone being attached to the ring and an ethyl, and that this was a Grignard. That works as well. So those are the two solutions. There really is another way.
What could we do maybe the benzyl with like 3 carbons with the benzene ring, and then what would be the double bond with one, two, like 3 carbons coming off one side?
Wait, could you repeat that?
Yeah, the benzene ring with 2, 3 carbons like coming off.
So like that?
Yeah, no, no, no. Like one, the
Oh,
primary.
oh,
Yeah,
yes.
and then a double bonded O attached to the same thing on the side, but like 2 of
This
them.
one?
Yeah, I guess that would work.
Oh, what are you talking about?
Well, I was talking about that actually. Wait. Actually, yeah, with the double bonded O right there, and then it's not. Yeah.
Yeah. So I see what you're doing here. So this is the same orientation that it is at above, but this is actually the same thing
Yeah.
that I
What if
drew.
you had the MGBR attached to where the O is?
Oh, so like if I took this out, okay, I see what you're saying. If I took
Yeah.
this out and I was like that?
Yeah.
Oh, okay. Would that work? No. Because you have to think through the mechanics of how that would work.
Hmm.
So, like, actually, it could work, right? Yes, it could work, right? Yes, it can work. Can it work, guys? My brain is shutting down a little bit. I think it can work. Um, yeah, so that might be another solution. Let's try it. So, in this third solution, we're gonna say, um, sorry, my brain is already shutting down. But yeah, I think that's a really smart way to think about it too. I think that could work. So if we did MGBR coming off of this, and then we had, yeah, that should work, right? Yeah, this works. Good job. Is that the solution you came up with?
Yeah, that's what I was thinking, except it's
Nice. Good
little.
job. Yeah, that's actually kind of like that's kind of cool. Um, yeah, so all three of these are good ways of doing it. So I guess like the thing that I'm learning right now is that what we said before isn't necessarily true. So you know before we said, oh, if it's a tertiary alcohol, it came from a secondary carbonyl. Remember that? But this is actually only a primary carbonyl. So, you know, it's something that you can use it, but also there's solutions that don't use it. So don't get discouraged if your answer doesn't follow that exactly. Do you see what I'm saying?
Yeah.
You know? So like it's something that you can use. You could just take it as a rule and make sure that your carbonyl is secondary. Again, make sure your carbonyl is secondary. Those are both secondary carbonyls. But you could also, there is possibilities for doing it primary too. But there's no such thing as having a primary alcohol that came from a secondary or higher carbonyl. So you could go lower, but you couldn't go higher. Does that make sense? I don't know, I think I'm confusing you guys. Lakshmi?
So I did something different. I was just wondering if it would work. So I did the benzene ring and then a carbon coming off of it, and then off
Mm-hmm.
of the carbon a double bonded O, and then it's connected to uh no, and then also off of that carbon I just
Mm-hmm.
did a single bonded O and then a CH3 CH2.
Oh yeah.
And then
Yeah.
I did 2 moles of CH3 CH2 MGBR. Would that work?
Wow, this is yeah, I think so. Yeah, that would definitely work. That's one solution. Okay, you guys are really opening up. I was literally like, there's two solutions, but you guys are coming up with so many. And another solution would also be to, yeah, yeah. So that's mainly that's another solution. Yeah, that works. And then you could really make that go different ways. So I think there might be like 10 solutions. So you could use this principle with an ester involved, and you could do lots of different things. But yeah, so I don't really see it. He did say what's the carbonyl compound in the Grignard reagent, plural, singular. But I mean, that is a really like a smart way of thinking about it too. And then going off of that, like from that point, you could really come up with different things, you know? So yeah, good job, guys. It's really good to think outside the box. Even though, like, I would say, like, you know, some of them are like more roundabout than they need to be. Like it's really, really good to like explore different things. Like sometimes when I look at retrosynthesis, I try to think of the most complicated and backwards way to do the retrosynthesis. Because it's like really helpful to think about things from different angles. All right, let's tackle this last one. All right. So for this one, um, so like this is a secondary alcohol, so we know that it would come from a primary ketone or less than primary, possibly. Okay. So what I mean by that is, well, our rule that we talked about, we had to kind of revise it a little bit. So this could come from primary or less. It couldn't come from more. There's no way this came from a secondary alcohol, but it could have come from a primary alcohol or a zero alcohol. So the primary alcohol option could be like this. So a hydrogen on one side, CH3 on the other side, and our square with MGBR there. So that would produce one answer. Another answer that would be less than primary would be like this, hydrogen, hydrogen on each side. So that's 0. It's like 0 degrees. And then this would be our Grignard, like that. So that's another option. Are you guys thinking of anything else? I'm curious to hear your ideas. I don't think you can do what Lakshmi did there last with 2 moles and an ester because you don't have enough things off of the alcohol has to be tertiary to do that. But it could have come from an ester. No, actually, no, never mind.
It could have. It could have been like a diester. But then it would be like two different Grignard reagents. Like for example, if there was like a CH3O and then it was connected to the carbon that had the ketone on it that's also connected to an O and then like another CH3.
Yeah, but in this case, oh, okay, so you're saying that, okay, I see. So let me reread this. So yeah, that would work. So,
Yeah.
so what JD is saying is like this, an ester on each side, whatever. So basically what happens is we're reacting it with this and also this. No, that's one too many. This. Okay. So when this first one comes along, so the first square with the negative charge comes along, attacks here, this breaks off. We get, no, that still wouldn't work because it would be left as a ketone.
Yeah, you're right.
Yeah, because then if we took this one, CH3, attacked it here, it would be left as a ketone. So we'd have this. Close, but not enough. We need to change this into an alcohol. I guess then we could attack it with, oh no, we couldn't. Never mind. Yeah, so that is really cool though, but it has to be left as a ketone for that to work. All right, any other solutions for this one? Okay. All right, we have 5 minutes left, so I'm gonna start wrapping up now. I will be here for like a couple minutes if anyone has any other questions. I'm just gonna tackle Nexus for a second.
I have just one quick question.
Mhm.
The LICU one function kind of like the same as the MGBR?
Yeah, basically. It's just a negative charge. So if we have like this versus this, I mean, they're both effectively, oops, they're both effectively this, you know?
Mhm.
The only thing is that they work in different situations. So they're both like nucleophiles, but this one has to react with a a ketone, basically. And this one has to react as like substitution. So if there's something with a bromine on it, it will substitute it and it will now become with a nucleophile on. Whereas like this one will become, does that make sense? And I don't know, is what I'm saying correct? My brain is like pretty much mush at this point. So I I I don't really I never really understood the overview of like Grignard versus Kubrick. I just did what was the correct thing to do. I didn't really know the names and stuff like that, but I think this is a way of breaking it down. The
Yeah, that
difference.
looks correct. I feel like there's really nothing else that was discussed in class about what is
Yeah.
exactly going on over there.
Right, exactly. We don't totally know everything, but this MGBR has to react with a ketone and Kubrick has to react with a leaving group. See, because this is not a leaving group, right? It's not leaving. Does that make sense?
Yeah.
Okay, perfect. That's a really good question. I really like when you guys had really good questions today, I must say, like, um, in Orgo 1, there were times when we did review and like I would just talk about random things, hoping that I was hitting something that would be useful to you guys. But you guys had like amazing questions this time. You guys clearly did your work before you came. I really, really appreciate that. That makes the session so much better for everyone. So we did tackle some really important topics today, because of your questions, which were very insightful. Um, so I really like, I hope you guys do amazing. I have a really good feeling about this exam. I haven't seen anyone so far who looks like they're struggling terribly. But if you are struggling, let me know because again, I don't know of anyone struggling in the class. So, but yeah, and then keep up the energy for exam two because we need it. We're gonna be doing NMR for the next exam. Um, it's something new and please, please, please start working on it like immediately after your exam's done tomorrow. Because it takes about 2 to 3 weeks for NMR to really set in. Okay, maybe one. So like 1 to 3 weeks for NMR to suddenly, for you to suddenly get it. So if you're someone who's going to take you 3 weeks to get NMR, you need to get started tomorrow because you need to know it before the exam. But yeah, not to worry you guys about the future. I'm sorry about that.
NMR party in here on Sunday? Yes, no?
Yes, absolutely. Let's tackle NMR this Sunday. If anyone's up for it. Of course, don't feel like you have to comp. You just took an exam. But if you comp, that's the reason Dr. Swan introduced it already, because you need to see it for a certain amount of time before you get it. So I'll be there on Sunday, and we can just kind of start talking about NMR and what it is and the tips for knowing it. Okay. So good luck, everyone. Um, I mean, tomorrow, if anyone has any really urgent questions, you can email me. Okay.